Hello, peer reviewer. My name is Elizabeth Williamson, and this is Lab 2, Motion of a Falling Object. This lab follows the observation of a falling object and its predicted data involving the force of gravity and drag. We will again start with the basic concept of Newton's second law. The basic formula for this is net force equals mass times acceleration. As opposed to the first lab, the net force in this lab is not zero as we are observing the object from rest, meaning that it accelerates as time goes on. This is shown through how acceleration equals the change in velocity over the change in time. Since Newton's second law is directly related to net force and inversely related to its mass, we can look at a variation of the law involving the weight force and the drag force. The drag force equals negative b, also known as the proportionality constant for the magnitude of drag times the velocity of the object. The weight force then equals the object's mass as a negative, which in this case was 0.011 kilograms, times the gravity's magnitude, which is 9.8, times j hat, which is the unit vector in the positive y direction. With this addition of weight and drag, we can observe how the net force affects the acceleration of the object. We can also quickly look at the velocity and position update formulas with the initial velocity being 0 because of the object starting from rest, as they help to find the predicted final position and velocity of the object. With these, we can compare and contrast the data from the predicted to the observed. Here is a slowed down video of the object, 2 plastic bags falling with the data points found in Tracker. Here we can see that it moves down the negative y-axis in a straight line. We can also visually confirm that the object is accelerating due to the spacing of the data points. This can also be confirmed due to the slight parabolic motion of the position time graph. I will also quickly discuss the code just so we can get a better idea of what is actually occurring as the object is falling. As previously stated, the mass was 0.011 kilograms, and both the initial velocity and position were 0 as the object began from rest. The value of the drag was found through trial and error, that is, after the equations for weight force, drag force, and net force were entered into the 0.733 second loop. The velocity and position update formulas discussed earlier were also added to the loop, as were gravity and drag arrows, to visually illustrate these forces. Here we can see the movement of the object down the y-axis with only the force of gravity acting upon it to begin with. The object began from rest and accelerated to a point of approximately negative 2.7 meters along the y-axis. We can also see that the object accelerated at almost a constant rate, as seen by the velocity time graph here. In this second set of graphs, we can see the movement of the object down the y-axis again, but this time with both drag and gravity. The object accelerates for a much shorter period of time here, as shown by the position time graph, and the velocity quickly increases at the beginning of the velocity time graph, but begins to even out towards the end. What does this mean? Well, the graph begins to illustrate a terminal velocity of the object as it falls downward. This is due to the fact that drag force and the force of gravity have basically equaled each other, meaning that the object is reaching a final constant velocity after acceleration and a net force of 0. This can be seen from not only the velocity time graph, but also the movement model to the left, as seen by the force arrows equaling each other, and the position time graph. Then again, what if the object was thrown down instead of dropped from rest? The object itself would accelerate much quicker because of the added force from the throw acting alongside gravity. This means that the velocity would increase faster and most likely reach the same terminal velocity, but much sooner due to the downward force being greater than the air resistance. Finally, we can compare all of the data that was collected over the course of the lab, with the blue line being the observed data and the orange line being the predicted data with only gravity. We can see that they are not at all accurate when compared to each other. What this tells us before we even look at the drag data is that the object that was tested has a considerable amount of air resistance. Without this other upward force, the object would be able to travel a lot farther down the y-axis as seen here. With this, we can compare and contrast the observed data with the predicted drag data. The data is similar in that the predicted and observed data both begin accelerating at the same velocity and both end at the same terminal velocity. They also both roughly follow the same parabolic motion along the graph. They contrast in that the predicted data reaches terminal velocity more quickly than the observed data, likely due to the sheer amount of drag being placed on the object, as this will not allow it to accelerate as much. This experiment could likely be improved accuracy-wise if one utilized an object with less drag and then also took into consideration the surface area and the shape of the object itself as it was falling. Thank you.